Today, we are going to find how to get a series representation of a function using integration. I'm choosing today the function natural log of 1 plus x. So obviously, since I don't have absolute value signs, I'm assuming here that x is going to be some number that's non-negative in this, or 1 plus x is non-negative anyway. Now, that looks like kind of a challenge because it's not very clear what's going on with it. But instead of doing integration, let's try for a moment to think about what does the derivative of the natural log going to look like. So if you remember, that's going to be just 1 over 1 plus x. Well, how is that going to help us in this particular case? Well, it's worth remembering that if we take the antiderivative of both sides, or the integral of both sides, the natural log of 1 plus x is equal to the integral of 1 over 1 plus x dx plus some constant c. Now that looks a lot more promising. The reason being that now we can focus in on our function 1 over 1 plus x. That's really similar to something that we have seen before. Namely, if we remember by using the geometric series idea that a over 1 minus r is going to be equal to something, we have our pretty standard series 1 over 1 minus x equals the sum from 1 to infinity, or 0 to infinity, sorry, of x to the n. And then if we changed it, so that 1 over 1 plus x, by that regular substitution, we know that's going to be just negative x to the n, or if I was going to be a little bit nicer about it, I want to take out that negative 1 to the n, x to the n. Now, honestly, I could do this problem if the negative 1 was there, but frankly, it is much easier to deal with if we just take that negative 1 to the nth power out. So remember, if we have a product, we're allowed to distribute the powers to it, but only if it's a product or a quotient. You can't do that regularly. So that being said, now we can start thinking about how to translate it by taking the integral. So when we differentiate, we can take the integral, when we take the derivative, we take the derivative term by term. We can do the same thing here. So what happens is that I can just substitute in the series that I found before and just do this. One of the interesting things is, like with differentiation, you're allowed to take it term by term, which means I can bring the integral inside. Now, in this particular case, I don't have to worry about that negative 1 to the nth power. Note the n is the index, but I'm integrating with respect to x. So be really careful about what you're doing with this, because you don't want to mess up what's x and what's n. It can really throw you off if you decide to start mixing up which is which. So what happens with that? Kind of our standard thing. This is reverse power rule. We know it's x to the n plus 1 over n plus 1. Let's not forget our negative signs. And plus c, which is what we standard. So remember, with derivatives, we reduce the index by 1 each and every time. When we use integration with a series, we're going to have a new constant every time. So if I integrated this again, I would have another new constant that came up. So you would say like, oh, but is this done now? It's like, no, unfortunately it's not, because we have to deal with this and say, what is the constant? The way to do that is to go back to the beginning. Try x equals 0. So then you have natural log of 1 plus 0. And then this is going to be 0 to infinity, negative 1 to the n, 0 to the n plus 1 over n plus 1 plus my c. So looking at this a little bit more carefully, you notice every single term here is 0. So you're 0 times a negative, well, that doesn't matter. 0 over n plus 1, well, that doesn't matter. So every single time that summation is going to give you 0, so that's just 0. Then you say like, well, but this is natural log 1 plus 0. Again, 0. So 0 is equal to c. So what we are going to get is the natural log of 1 plus x is going to be equal to n equals 0 to infinity, negative 1 to the n, x to the n plus 1 over n plus 1. And remember, c is 0, so this is the answer. So there's one more thing that I need to talk about, and that is I want to say what the interval of convergence is going to be, which I have not given an example of in a video. At least not yet. So remember, the focus is on this series here. It is not on that natural log of 1 plus x. So we have to say like, well, where can we go? So like with anything else, when you talk about this, we have to do the ratio test on this particular series. So our standard rule, ratio test, and I am going to include the absolute value because we do have a negative sign involved in this. So that's the a sub n plus 1, being careful about how this works. And I'm going to do kind of the shortcut style to say at least one line and do this. So when I get rid of the absolute values, I can certainly get rid of all the negatives, and it simplifies very nicely to x times n plus 1 over n plus 2. Note n plus 1 over n plus 2, that's going to go, I can take out the absolute value of x, like so. Note that the limits itself, this whole thing here, is just 1. So we have the square root of the absolute value of x times 1, which is just absolute value of x. This is less than 1 for convergence. You don't have to write for convergence. I'm just writing it because some people in the past have been a little bit confused about what that exactly means. And then I can check for, that's just the radius of convergence. Okay, because it's the absolute value of x strictly. Now I need the interval, so I'm going to get negative 1 less than x less than 1 to check the interval. So x equals 1. When I go back and check my series, that means I have n equals 0 to infinity of negative 1 to the n over n plus 1. This is an alternating series, so I can do the alternating series test on this. So b sub n is equal to 1 over n plus 1, 1 over n plus 2, which is equal to b sub n plus 1. That's going to be less than 1 over n plus 1. So that's the first part. And I think pretty clearly limit as n goes to infinity of 1 over n plus 1 is equal to 0. So it converges by the alternating series test. X equals negative 1. This is a little bit more complicated, but not really. Negative 1 to the n over n plus 1 times negative 1 to the n. Now, in other words, whenever n is always the same for the two points, so they're either both negative or both positive. So even if they're both negative, they're going to cancel each other out, and you're going to get just 1 over n plus 1. This is going to be a limit comparison test. You might need a little bit more time to figure this out. But the idea is 1 over n is a divergent series. Because it's a p series, it's the harmonic series. And if we take the limit as n goes to infinity of 1 over n plus 1 times n over 1, that's going to be just 1. So the limit comparison test applies. So this implies both series diverge. And the interval of convergence in this particular case, I'm going to not include -1, but I am going to include +1.